I posted the next assignment, number 6, week to do, and it's exactly the same problem that we did in class, creeping flow, but over a fluid sphere. So the sphere is also fluid, but you assume it to be maintaining its shape. It's not deforming as the fluid, another fluid is flowing past it. So it's basically an opportunity for you to work through all the mathematical details that we went through in class for a solid sphere, but twice, once for the inner sphere, one for the outer sphere, and then go through the solution for the stream function, for the inner one, outer one, get the stresses on the surface, and show that the drag force is given by this expression, where sigma is the ratio of the viscosities, the two viscosities. So you will notice that as sigma goes to 0, I think sigma, did I define it? Yeah, mu O over mu I. So sigma goes to 0 means that the inner fluid viscosity goes to infinity. That means it's a solid. It's behaving more like a solid. And you get the original result that we saw, 6 pi mu u A. Now if sigma goes to infinity, what does that mean physically, and what happens to that expression? Sigma is a ratio of the outer fluid to inner fluid. Okay, so if sigma goes to infinity, that means the outer fluid viscosity looks much larger than the inner fluid viscosity. So it's as if the inner fluid is a gas bubble, for example. Okay, so its viscosity will be very small. So in that limit, it will go to, I think, the 1 and 1 will cancel when sigma is very large, and you'll get 2 over 3 sigma over sigma. So it will become 2 over 3. So it will go to the limit of 4 pi. And this is called the Smoluchowski result, which was developed by Smoluchowski for the first time. So the basic idea is to give you an opportunity to work through all the math details on a problem that looks very similar. Now the second part of this problem is back to solid sphere, but now using COMSOL. Okay, here I'm just testing your ability to build on COMSOL based on what you've already seen. So there are two cases. One is a cylinder, another is a sphere. In both cases, when you're building the geometry, you will just take a circle and put it there. Now, if you choose the 2D axisymmetric, that circle becomes a sphere. If you just pick 2D, then it becomes a cylinder. Okay, so I want you to solve that for a whole range of Reynolds number, 0.1, 1, and 20, and calculate the drag coefficient in each case and compare it with the analytical result and see how far they agree. And when you go to Reynolds number of about 20, you will already begin to see the wake. And I want you to capture a picture of that and include it in your assignment. Okay, so it should be fairly straightforward, but just repeating what we did in the class for the first part. So any questions for me? Okay. We're going to continue with the potential flow today. But let me just briefly review what we saw in the last class. That is, we showed that the Stokes solution is not uniformly valid, and you should understand what that concept means, that it's not valid over the entire domain. Okay? It's a better approximation near the sphere than far away from the sphere. And a low Reynolds number flow, the influence of the sphere is felt many, many diameters away from the sphere. We saw that both in the film by G.A. Taylor and an order of magnitude analysis to show that the creeping flow solution is not uniformly valid. Then we saw attempts to extend the validity of the solution beyond a Reynolds number of 0. And here we introduce this idea of a regular perturbation expansion process, how to linearize a nonlinear problem and build a series of linear problems, each one of which can be solved relatively easily compared to the nonlinear problem. And we saw another way of linearization, which is the Ausseen method, which is more ad hoc. The first one has some formal structure to it. The second one is I'm just going to decompose the velocity into a main velocity u under perturbation and ignore all the perturbations around it. And he was able to derive and solve the Stokes, the extension of the Stokes problem to get a correction to the Stokes flow. And then we saw what is a Stokes paradox. Does anybody remember what a Stokes paradox is? Non-existent, exactly. Okay. So in the final exam, make sure that some of these concepts you're able to explain in simple words. I'll put the first question is just checking simple answers like that. What do we mean by a Stokes paradox? What do we mean by D'Alembert's paradox and things, stuff like that. And then we started looking at ideal fluids. The Euler equation is an important one, which is a subset of the Navier-Stokes equation where we have the continuity and the momentum equation. But in the momentum equation, we have assumed the viscosity of the fluid to be 0. Ideal fluid, so there is no viscosity, there is no viscous resistance to it. So the only forces that will balance are inertia, pressure, and gravity. And that is what gives rise to the Bernoulli equation. And we saw a Kelvin's theorem which states that in an ideal fluid, the condition of irrotationality is always satisfied. That means the vorticity is 0. That is, if you set an ideal fluid in motion, you can never stop it, but you can never get it to move unless you apply only normal stresses, because tangential stresses cannot cause the fluid to move in that idealization. There are no real fluids that obey that kind of a behavior. But the solution to the Euler equation gives us reasonably good pressure distributions from which we can calculate lift forces in aerodynamic designs, for example. The reason it is called the potential flow, we saw, is because I can define the velocity as a gradient of a potential function. So we have seen stream function before, we have seen vorticity before. We are now introducing a new function called the velocity potential. So it's some scalar function of three-dimensional space, and the gradient of which gives the velocity, and it automatically satisfies the condition of irrotationality by that identity that you see here, del cross del phi equal to 0. But we still need to satisfy the continuity equation. So this will satisfy the momentum equation, the condition of irrotationality coupled with definition of the velocity through the gradient of a potential function will automatically satisfy the momentum equation for us. The momentum equation without the viscous term, the Euler equation. But we still need to satisfy the continuity equation, so we take that definition, put it in there, del dot v, so del dot phi, which is del square phi. So now we get a handle on how to get that function phi. Here we just introduce that function phi as some scalar function, the gradient of which gives the velocity. But how do I get that function? We defer that question, and now we see if we satisfy the Laplace equation, any function that satisfies the Laplace equation will automatically give you the velocity field through its gradient and will automatically satisfy the condition of irrotationality, so you have a solution. So once again, we are able to reduce the potential work problem, 3 momentum equation and the continuity equation, to solving a single equation, a single linear equation, luckily for us, that will give us the velocity profile. Once, of course, we get the velocity profile through the definition, we can take the velocity profile and plug it in there. And we can calculate the pressure profile out. We need to get the velocity profile and pressure profile. Remember, these are the 4 variables, 3 velocity components and pressure. So we can get the pressure profile from the momentum equation. And we saw that if we take the Euler equation and dot it with the velocity vector, we dot a force term, that is your energy term or the work term. So that gives us the condition that because of the condition of irrotationality, this is equal to 0. So the meaning of del v dot del is following the motion of a fluid particle in a Lagrangian frame. Whatever that appears in this parenthesis is conserved because its gradient is 0. It doesn't change along that line. So that gives us the interpretation that along a streamline, this quantity in the parenthesis is a constant, so that its derivative is 0. And that is how we are able to integrate the momentum equation analytically and get the Bernoulli equation. So Bernoulli equation is valid only for ideal fluids. Okay? And then we empirically modify it by adding a friction term, a work term, etc. In an undergraduate fluid mechanics course. Now I want to focus attention on two-dimensional potential flows. Basically, my goal is not to solve differential equations, because solving differential equations is time-consuming and difficult part. Okay, so we always, if we have a PDE, we use separation of variables, we use similarity transformations to get it into an ODE, because I know how to solve ODEs. Okay, so in the same way, what I'm going to do now is devise a procedure whereby I take algebraic expressions, and I know those algebraic expressions are solutions to some potential flow problem, and so I invert the problem, ask the question, for what geometry would this function, analytical expression, algebraic expression that I have, be a solution to the potential flow equation? So I'm going to invert the process. But the logic to do that requires us to use complex variables. Anybody who has not seen complex variables at all? All of you have seen it, right? So we'll go through it very quickly so that you recall what you have seen, and then we will use that to develop the solution procedure for two-dimensional potential flows. Remember, the moment I say 2D, the thing that should strike you is you can immediately introduce a stream function. Definition for a stream function, which automatically satisfies the continuity equation. Okay, so here V1 is d psi dx2, and V2 is minus d psi dx1. It's exactly the same as the one we saw for the previous problem in Kriving flow regime 2, because it's just a definition of a stream function that automatically satisfies the continuity equation. So by potential function, I found out the Laplace equation will satisfy both continuity and momentum, Euler equation. I want to see whether I can do the same thing from stream function. So if I define the stream function, this automatically takes care of the continuity, but I still have to take care of the condition of irrotationality. That is Kelvin's theorem. If I satisfy condition of irrotationality, I've satisfied Kelvin's theorem, I've satisfied the momentum equation, Euler equation. But in two-dimensional flow, which vorticity component will be 0? Remember, what is the definition for vorticity? Vorticity omega is del cross V. Okay, and when you're expanding it, you're going to expand it something like I, J, K, the three vectors, and then dx, dy, dz, and then u, v, w. That's the expansion of the vorticity vector. Now, in a two-dimensional flow, what we know is that the velocity vector looks like this: v1 as a function of x1, x2, and v2 as a function of x1, x2, and v3 is 0. Right? So under those conditions, if you ask the question, what is the first component of the vorticity vector? How would we get that? Remember, it is dy of w velocity, and then dz of v velocity. That's going to be 0. Why is it 0? Because we have the third velocity component w as 0, and when you take the derivative of the second velocity component v with respect to z, the v component is not a function of z. Are you following me? Okay, so that component is 0. What about the second one? J. For this one, I would use this with this, and that with that, cross multiply, right? So the second vorticity component, omega 2, would be ddx of w. W again is 0. Or ddz of u. Again, u is not a function of z. So that vorticity component will also be 0. So in a two-dimensional flow field, the only vorticity component that is not 0 comes from the third one. Okay, that is using these cross products. So when you expand that, this is what you will get. Omega 3, the third vorticity component, is ddx1 of v2 minus ddx2 of v1. Of course, v1 and v2 are not 0. They are functions of both x1 and x2. So that will be not 0. Okay. So condition of irrotationality means the two vorticity components are already 0. I must make the third vorticity component as equal to 0. Okay. So this is the definition for the vorticity of the third component of the vorticity. So I take the definition for v1 and v2 and put it in there. So I get minus d square psi dx1 minus d square psi dx2, which is minus del square psi. That is equal to 0. So what this means is, if I can get a solution to the Laplace equation, once again the Laplace equation, I can call that as my stream function, and by putting it into the definition of the stream function, I can get the V1 and V2 component, and it will automatically satisfy the what? Condition of irrotationality, right? It will automatically satisfy the omega 3 equal to 0. So I have two ways of solving the potential flow problem. Either by solving del square psi equal to 0 and say psi is my stream function, and it will satisfy the continuity equation, and it will satisfy the condition of irrotationality, and V1 and V2 I obtain through this definition, these defining equations for stream function. Or I can solve a Laplace equation and take its solution to be, interpret its solution to be potential, velocity potential. And then I get the velocity components as gradient of the potential. And I will automatically satisfy the continuity as well as the Euler equation. So there are two alternate ways of getting the solution to the 2D potential flow problem. Any questions on that? Are you understanding the argument, the logic, the idea behind what I'm talking about? Okay, so there are two functions we can define, potential function and stream function. They're both solutions to some Laplace equation. And we have to define the geometry, of course. We have to solve the Laplace equation in some specific geometry. And then we take those and get the velocity field either from the stream function definition or from the velocity potential definition. But the beauty about this is we don't even have to solve the Laplace equation. So solving Laplace equation is solving a partial differential equation, right? You need to use separation of variables, etc. And for complicated geometries, it can be challenging. So what we are going to do is draw on complex variables, the theory of complex variables, which allows us to get solutions in a very simple way. Okay. So remember, the definition for stream function was V1 equals minus d psi dx2 and V2 equals minus d psi dx1. That was the definition. Now the definition for the velocity potential was V1 is equal to d phi dx1, gradient of a potential function, and V2 equals d phi dx2. Okay. Now, since you have seen complex variable, what does this equation remind you of? Those are the Cauchy-Riemann conditions for a complex analytic function. Okay. What does this mean? It means the following. If I have a complex function f of z, complex function will have a real part to that and an imaginary part to that. So I treat phi as the real part of the complex function and psi as the imaginary part of the complex function. So I put I here. That tells me that psi is the imaginary part. And both phi and psi are functions of x1 and x2. And we're dealing only with 2D flows. Okay? And z itself is the variable. So f is a function. That function is a function of z. Z is a variable, but it is a complex variable. It's not a real. So it is defined as x1 plus ix2. Okay? So we say that this function f of z is analytic when this Cauchy-Riemann condition is satisfied. That function f of z is continuous. Function f, which is a function, a complex function f, which is a function of complex variable z, is continuous with respect to z. There are no discontinuities in the field. Okay? Then these two conditions must always be satisfied. Okay? There is a real part. If you take the real part derivative with respect to x2, you should get the same thing as the phi with respect to x1. Or if you take psi with respect to x1, it should be minus of phi with respect to x2. And the other thing that we can show is that del dot the gradient of phi dot gradient of psi will always be 0. Okay? What does that mean? Well, for a two-dimensional case, gradient of phi is defined as I1 d dx1 of phi, I2 d dx2 of phi. That's the definition, right? The gradient function. Similarly, for psi, it's a gradient of psi. Okay? So I'm taking the dot product between these two. And when I take the dot product, I will get I1 dot I1, which is 1. So that gives me d phi dx1, d psi dx1. If I take I1 with I2, what will I get? 0. As I'm talking, I'm hoping that you will keep thinking in your mind, and when I stop, your thought process should continue, right? Because you're just not listening passively. You should be listening actively, okay? I1 dot I2 should be 0 because they are perpendicular to each other, right? I1 and I2 are unit vectors in the x1 and x2 direction. So when I take this product, I'll get 4 numbers, 4 terms, and only I1 dot I1 will be 1, I2 dot I2 will be 1, I1 dot I2 will be 0, and I2 dot I1 will be 0. So I get d phi dx2, d psi dx2, okay? Now I use the Cauchy-Riemann condition, okay? So d phi dx1, if you remember, d phi dx1 is the same as d psi dx2. That is, this first term here is the same as d psi dx2. And similarly, d phi dx2 is the same as d psi minus d psi dx1 from the second equation there, okay? We already established that. This line we already established by simply the definition, because V1 is defined either as gradient of phi, the two blue things that you see, or as d psi dx2, or V2 as minus d psi dx1. Because V1 is the same or V2 is the same, you have 2 ways of calculating V1 and V2. One is through the potential function, the other one is through the stream function. So using that, you will see that this is equal to 0. What does that tell you? This statement that gradient of phi dot with gradient of psi is always equal to 0. What does that tell you geometrically? They are perpendicular. Which are perpendicular? What are perpendicular? Which 2 entities are perpendicular? The gradient of psi, what does that tell you? The gradient of psi tells you the direction in which psi is changing the most. Okay, and similarly the gradient of phi tells you the direction in which phi is changing the most. So if I plot a contours of stream functions, for example, these are psi 1, psi 2, psi 3, and then another contours of phi, these are phi 1, phi 2, and phi 3, at every point of intersection, the 2 vectors that are tangent to this or normal to that, okay, they must be perpendicular to each other. So they actually form a nice coordinate system, orthogonal coordinate system, the stream functions and the potential functions. But the basic geometrical concept that you should take away from this is when gradient of phi dot gradient of psi equal to 0, that means they are orthogonal to each other. Contours of streamlines and contours of potential lines are perpendicular to each other. Okay, any questions? So here I have basically summarized in cylindrical coordinates the equations, okay, the continuity equation, the condition of irrotationality, the vorticity, and the definitions for UR and U theta in cylindrical coordinates. We have already seen that in Cartesian frame, but here I'm summarizing it in cylindrical frame. You should be able to work with both of them. And so we have del square phi equal to 0, del square psi equal to 0. What is the expansion for del square in cylindrical coordinates? Well, here it is, 1 over r d dr or d phi dr plus 1 over r square d square phi d theta square. Okay, so in cylindrical, in Cartesian frame, this would be simply d square phi dx1 square plus d square phi dx2 square equal to 0. Okay, and similarly for this one, d square psi dx1 square plus d square psi dx2 square will be equal to 0. You should be able to work on either one of those coordinates. Now we're going to digress to recall some of the important results from complex variables so that we can use that Cauchy-Riemann condition in solving potential flow problems without having to solve any differential equations. Okay. So what is a complex variable? Complex variable is any variable that has a real part and an imaginary part. Okay. So here I can label this as x and this as y coordinate. So x plus iy represents a point. Okay, so a pair of point I will simply give as xy, where x is measured on the real axis and iy is measured on the imaginary axis. Okay, the modulus of x is the magnitude of that vector. Okay, so sometimes we write it as simply between 2 parallel bars, as you see here. That is the modulus of a complex variable, which is the magnitude, which is square root of sum of x squared plus y squared. So geometrically, it means the length of that particular vector. Okay. The complex conjugate is defined as x minus iy with a over bar. So z bar simply means that it is a complex conjugate of the original one, x plus iy. Okay, so z bar, the product of that is equal to the square of the magnitude of the vector. In polar coordinates, that is in cylindrical coordinates, all you have to do is apply the coordinate transformation. X is equal to r cos theta, y is equal to r sin theta. So you replace x and y by r cos theta plus I sin theta, and r you can take as a factor, and cos theta plus I sin theta, what is that? That is e to the power I theta. This is another result that you need to recall. Okay, we will use that quite often. E to the power I theta is the same as cos theta plus I sin theta. It's called the Euler's formula. Okay, now we have just introduced what a complex variable is. Okay, how to represent complex variables. It has a real part and an imaginary part. And z is a complex variable. It is written as x plus iy. Now we're going to talk about complex functions. Complex function is a function. What is a function? Just a mapping from one variable to another variable. Okay, so here the variable, the independent variable is z, which is a complex variable, and f is a rule that maps a point in the xy space to another point in the real and imaginary part of the complex function. So the function itself is also going to be complex. For example, if I take z to the power n, z is a complex variable, z to the power n is a function. So I can replace this by x plus iy, and then, or I can replace this by r cos theta plus I sin theta. I can do this in either Cartesian frame or in cylindrical frame. And using the another identity, cos theta plus I sin theta to the power n is cos n theta plus I sin n theta. If you're doing the expansion of x plus iy, it has to be a binomial expansion, okay, to the power n. So that is an example of a complex function, z to the power n. We will come back and use that later on, n equal to 2, n equal to 3, n equal to 4, etc. Another example is e to the power z. So z still is a complex variable, but e to the power z is an exponential function. And the definition for that is the same series expansion, z to the power n over n. But this is z square, z cube, etc. So you need to substitute wherever you have a z, x plus iy, if you want to separate the real and imaginary part, which we will always want to do. Why? Because in a potential flows, x and y are going to be the two coordinate systems, and the real and imaginary part of a complex function is going to be your stream function and velocity potential. Okay, so we're going to make that connection, and then we just have to examine various types of complex variables. Now, this idea of an analytic function. What is an analytic function? A function is said to be analytic if it has unique derivative. So that when you're taking the derivative of the function, it must be unique, independent of which direction you are approaching that derivative, in the x direction or the y direction. Okay. So we're going to say the real and imaginary part of that function be u and v. We have been calling it so far psi and phi in potential flow theory, but this is just complex variables. So u and v are two complex, the real and imaginary part of a complex function. Okay, so f of z is equal to u of xy plus iv of xy. Think of it as simply phi and psi, phi plus I psi, for example. So when I say calculate the derivative of that function f with respect to z, what do I mean? The limit process, right? So the limit delta z going to 0, f of z plus delta z minus f of z divided by delta z. That is how I define the derivative of any function, real function. I am applying the same definition to complex function also. So the meaning for the derivative of this function is I calculate this function in the limit of delta z going to 0. Okay, so the numerator I'm going to call as delta f. That is f calculated at x plus delta z minus f calculated at z. So I call it as delta f. Now delta f is going to be complex. So I'm going to have a variation in u and a variation in v. Similarly, delta z will have delta x plus I delta y, I guess. Just the I there. Right? So I'm decomposing both the numerator and the denominator into its real and imaginary part. Okay, so what I want to do is I can calculate this derivative in a number of ways. For example, this is xy space, and I have another space where I have u and v. Okay, so for every point z is a point in the xy space. So I take the x value and y value, put it into this function u, and put it into this function v. I calculate u and v. Okay, that gives me a corresponding point in the uv space. So function, as I said, function is a mapping from one space to another space. We are used to the function of a scalar variable f of x. X is one line, and then we plug in the definition for x into f, calculate it, and you get a curve. But here what happens is for every point in the complex plane xy, I will get a corresponding point in the complex function ub. Okay, and the recipe is very clear, because if I tell you what u and v are, you can select a series of xy values, plug it in there, and plot the corresponding one. But what we want to do is evaluate the derivative of this function at a particular point. So I can calculate the derivative either by perturbing in the u direction only or in the v direction only. So the point is, whichever direction I take, I should get the same value for the derivative at a particular point. If the function is analytic, if the function is continuous, the derivative must be unique, no matter how I calculate it. So I do it two ways, and this gives me, when I do it two ways and insisting that they must be the same, gives me the Cauchy-Riemann condition. So the Cauchy-Riemann condition is no magic, it simply falls out of this condition that the function must be analytic. Okay, so follow this logic. So I'm parallel to x-axis, delta y is 0. There is no variation in the y direction, in the perpendicular vertical direction. So I'm considering only variation in the x direction. Okay, so this formula will become u plus I delta v in the numerator, but in the denominator, since I have already set delta y equal to 0, I have only variation in delta x that is possible. Okay, and so in the limit of delta x going to 0, this becomes partial of u with respect to x plus I times partial of v with respect to x. Follow this carefully, okay? Or do you understand what has happened here? I've calculated the derivative d of dz, but in a way where I've specified delta y is equal to 0. That means I've set this equal to 0. Okay? So denominator I have only delta x. Then delta u over delta x in the limit of delta x equal to 0 is du dx. Plus I times delta u over delta x, delta v over delta x as delta x equal to 0 is dv dx. Okay? That's basically applying the limit, the definition of a limit. Next, I do fix the delta x is equal to 0. So I'm varying delta y. I'm calculating the derivative, approaching that point, the same point. The derivative is evaluated at the same point, but approaching in the y direction. Okay, there is no variation in the x direction. Then I will get I delta y in the denominator. Okay, and so I get limit of delta y going to 0, delta u over delta y, that is du dy. Now, why did I put a minus I here? 1 over I, right? So 1 over I, so I just multiply and divide by I. So it becomes I square is minus 1. So I'm left with an I in the numerator. Okay, the next term, both the i's will cancel out. So that will give me the real part, dv dy. So now I insist that this derivative and this derivative must be the same, because I'm calculating the derivative at the same point, just two different ways. And that means the real part in here must be the same, and the imaginary part in here must be the same. So du dx must be equal to dv dy, and dv dx is equal to minus du dy. And that is the Cauchy-Riemann condition. Okay? So, to summarize then, if you are solving the Laplace equation, okay, the Cauchy-Riemann condition will also mean that they automatically satisfy the Laplace equation. So if you have two variables that satisfy the Laplace equation, then they will give you, the real part will give you the psi, and the imaginary part, the real part will give you the phi, the imaginary part will give you the psi. So you don't really need to solve any differential equation. You can take a complex variable, and that complex variable function is going to be a solution to some potential flow problem because it will satisfy all the sets of conditions: continuity equation, Euler equation, and the Cauchy-Riemann condition. That is the connection between complex variables and potential flow. Any questions on that? Okay. So to summarize, take any complex function that is analytic, that means it has continuous derivatives, no discontinuities in the function, separate it into real and imaginary part. The real part will give you the potential function. The imaginary part will give you the stream function. And they will satisfy the Cauchy-Riemann condition, they will satisfy the Laplace equation, they will satisfy the Euler equation, continuity equation, everything. Now, one more thing to notice is if I take such a function that is given a function f of z, if I take its derivative with respect to z, okay, and look at the derivative of the function, its real part will be v1 and its imaginary part will automatically be v2. So this is called the complex velocity. The velocity is not complex, it's a complex variable, but its real and imaginary part gives you the velocity components, and it is simply the derivative of that complex function, analytic function. Okay, that's another result that we will use. That is given, I will give you a function, a complex function, and then say find its velocity field, find its stream function, find its potential, find its pressure distribution from there, etc. We'll do a few examples that will make it clear. So when you're dealing with Cartesian frame, this is fine. Okay, you can take the derivative of this f with respect to x1, and you can get the velocity components. But if you want to do it in polar coordinates, r theta coordinates, cylindrical coordinates, then what you need to do is use the transformation. The v1 equals vr cos theta minus v theta sin theta, coordinate transformation, and v2 equals vr sin theta plus v theta cos theta. Okay, but we know that df dz is given as v1 minus v2. Okay, so take this v1 and plug it in there, and take that v2 and plug it in there. Okay, so v1 becomes vr cos theta minus v theta sin theta, and v2 is this. And combine them, that is, take vr as a common factor from both, and then v theta as a common factor from both terms, and you'll get cos theta minus I sin theta in both terms, and that is nothing but e to the power minus I theta. Cos theta minus I theta, minus I sin theta is. So what this tells us is if I take the derivative of that function f that I give you, and then extract this factor, and this is key, okay, extract this factor e to the power minus I theta, whatever is left, split it into its real and imaginary part, and its real part will automatically give you the velocity component in radial coordinates, and its imaginary part will give you the velocity component in the theta direction, in the cylindrical coordinates. Okay?
Will you say automatically?
Yeah, automatically meaning the interpretation for those would be that its real part is VR and its imaginary part is V theta. So the procedure that we are going to do for solving potential wave problems is take some complex function and do the analysis. So in the first example, I'm giving you the complex function is f is equal to uz. U is a constant, a real constant. Z is a complex variable. Analyze for what problem that could be a potential flow solution. That's how the problem will be stated in an exam. Okay, I give you a complex function and then say analyze for what problem, for what geometry this could represent a potential flow solution. And the procedure that you would do is basically the following that we are going to do. So you'll use the definition for z, which is x1 plus ix2. So f of z is u times x1 plus ix2. Now I can separate this into the real part and an imaginary part, ux1 plus I times ux2. So the real part gives me what? The real part gives me phi, the stream function. For the function f, the analytic function, I separate the function into its real and imaginary part. The real part gives me phi. and the imaginary part gives me psi. So I already know what is the potential for this particular problem. The velocity potential is u times x1. What is the stream function? The stream function is u times x2. How do I know that? Because you told me that the function is uz. So I simply separated that. I substituted for x, z, in terms of x1 pi x2. I separated the real and imaginary part. So the real part is my phi and the imaginary part is my psi. Okay? Now, how do I get velocity, v1 and v2? Well, I could use either the definition for phi. So I take phi and take its derivative with respect to x1. What is the derivative of ux1 with respect to x1? U itself, right? So here I'm substituting for phi ux1. U is a constant. So dx1 with this dx1 will be just 1. Okay? Or I can take psi and put it into its definition. So v1 would be d psi dx2. That's the definition. But psi is ux2. So when I take the derivative of that with respect to x2, I still get u. So whether I use phi, the velocity potential, or psi, the stream function, I get the same velocity. Of course, it must be true because Cauchy-Riemann condition is true, right? So v1 is the same expression u. What is v2? v2 from the definition for the potential function is d phi dx2. But is phi a function of x2? Phi is not a function of x2, right? Phi is a function only of x1, you see here. So it is 0. Similarly, I can take psi and put that into this definition to calculate the same v2. v2 is minus d psi dx1. But psi is not a function of x1, so that is 0. So we already know what phi is, what psi is, what v1 is, what v2 is. At this stage, you start sketching out what could this velocity field look like. How would it look like? This is x1, that is x2. So v1 is u, right? So it is pointing in this direction. The velocity is pointing only in the x1 direction. There is no velocity component in the x2 direction. The velocity is just u everywhere, constant. Okay, I should actually draw the same vector length everywhere. So it is a uniform flow. A uniform flow in the x1 direction. Okay, so suppose I put a plate here. Will it affect the velocity field? I put a plate there. What would happen? What would happen in reality and what would happen for an ideal fluid? In reality, there will be a boundary layer because the fluid must stick to the plate. The plate is not moving. But ideal fluid will simply slip past it. So you would not, the ideal fluid will not even notice the presence of a wall there. Okay, so you could take any of the streamlines, and these are all streamlines, right? This is the velocity vector, but that's also the streamline. How do you know? Because what is streamline? Stream function, psi u times x2. Okay, so if I, for example, what would this streamline be? Psi is equal to 0 because x2 is 0. This is the origin. And if x2 is 1, then this will be psi is equal to 1. If there is 2, then this will be psi equal to 2, etc. Because psi is simply u times x2. I guess I should put 1u and 2u, etc. Okay, so any of those streamlines could be a boundary, and the ideal fluid will not know its presence at all. It will just slip past. Okay. Well, there is another way of getting the velocity, and that is through the complex velocity. Given f, I can take its derivative. Remember, f is given as u times z. If I take its derivative df dz, what will it be? U, right? But that must equal v1 minus iv2, because that is how complex velocity is defined. The derivative of that function is your complex velocity. So the real part of u will give you v1, and the imaginary part of that expression will give you v2. So you can see V1 is simply, because there's only real part, there is no imaginary part. So V2 is equal to 0, V1 is equal to U. Okay, so I said let's sketch the plot, and here I'm showing how to do it with Maple. So you enter the command once you start Maple with plots, and it will spit out all these statements, and then you say contour plot. Contour plot of 2y. I'm plotting the contours of stream functions. Stream function is ux2. So I'm picking u as equal to 2, and x2 is the same as y. Okay, so I'm saying plot me the contours of 2y over a range of x from 0 to 0.5, 0 to 5, and y from 0 to 5. Okay, and that will generate the contour plot. We have already talked about how to generate contour plot if you have to do it by yourself. So that is a graph that it gives. So all the streamlines are horizontal. The velocity vector is along the same direction as the stream function. Okay, so these will be the stream function values: psi1, psi2, psi3, etc. These are contours, and those are the velocity direction of the velocity vectors. So the function f is equal to uz gives you uniform potential flow in the x1 direction. That is the interpretation that we give. We have never solved any differential equation, okay? Because this function will automatically satisfy all the conditions that needs to be satisfied. Okay, it will satisfy the Laplace equations, it will satisfy the continuity and momentum equation, etc. Any questions on that? This is too trivial an example, so you may not really fully appreciate the power of this. But if you want to calculate the pressure, what do? Once you know the velocity field, you put it into the Bernoulli equation, because Bernoulli equation is the integrated form of the Euler equation. Okay, so once you know the velocity, we'll plug it in here, and you can calculate what the pressure field is. Okay, of course, G is the gravitational field that is known, so you can calculate what the pressure field is. Next example, slightly more complicated example. This time the analytic function is given as f of z equals u e to the power minus I alpha z. Here, u and alpha are both real constants. Alpha is a constant, u is a constant. We don't know what those constants mean yet. We need to do the analysis and then give it a physical meaning, attach a physical meaning to each one of those constants appearing in that expression. So right now it's just a complex expression, complex function. It is still a linear function in z. Okay. So the process is the same. Separate it to get the real and imaginary part, to get phi and psi. Then take the derivative, separate it to get the u and v, u1, v1. Okay. Or you can take the derivatives of the stream function and velocity potential. Any method that works. There are three methods of getting the velocity components: from the complex potential, or from phi and psi by using it in the defining equations for phi and psi. But the first thing that we need to do is expand it. So u e to the power I z is u times cos alpha minus I sin alpha. Again, these formula you don't have to remember. I put them in the formula sheet for complex variables, the relationship, something like e to the power I alpha. You don't have to remember. Just use, it's in the formula sheet, cos alpha minus I sin alpha. Of course, z is equal to x1 plus ix2. Okay, so we have now a complex product of two complex expressions. Okay, so you need to take the product and separate them into real and imaginary part. So when you do that, for example, u times cos alpha times x1, okay, cos alpha and x1 cos alpha, that's the real part. And then when you do I sin alpha and ix2, what will you get? I squared sin alpha x2, but I squared is minus 1. So that's also real. That's where you get this, x2 and sin alpha. And when you take cos alpha with ix2, you get a part of an imaginary part, right? So there will be x2 cos alpha, x2 cos alpha. Okay, and when you do which one is that? I sin alpha with x1. That will also be imaginary. Okay, that gives you x1 I sin alpha. So there are four terms, but they are regrouped. So one grouping the real part, the other one grouping the imaginary part. So the real part gives you phi. So the phi is going to be this part. Okay, and the imaginary part gives you the stream function. Now you can map, you can control it. You can go to Maple and then ask it to plot. What do you think? Let me ask you to imagine, and how will the stream functions, and maybe you should get the velocity field first. That might help. So to get the velocity field, as I said, you have a number of options. One is using the definition, d phi dx1. v1 is d phi dx1. I already know what phi is. So when I put that and take the partial derivative, I'm going to get u cos alpha. x2, the derivative will be 0. Similarly, v2 will be u sine alpha. And you can get the same thing by taking f df dz, okay, which simply leaves you with e to the power minus I alpha, which is u cos alpha minus I sine alpha. So the real part gives you u, the imaginary part gives you the v1 and v2 components. Am I going fast? Are you guys following me? If I'm going fast, you need to slow me down. Okay, so now with that information, how does the velocity field look on an x1, x2 coordinate or xy coordinate? And what is the interpretation for u and what is the interpretation for alpha? Both are constant numbers. So fix alpha as a number. How would the velocity field look? Here I'm going showing with an example. Okay, alpha is 45 and u is 1. So the stream function is minus x sine alpha, which is you see here, plus y cos alpha, which you see here. And then I'm saying plot it for x between 0 and phi and y between 0 and phi. And you can see the graph and ask, does it make sense? What are these? These are contours of stream function, right? So this would be psi 1, psi 2, psi 3, etc. because that's what I'm plotting. So that means that the velocity vectors are all pointing in this direction. So what would be the x1 component? And what would be the meaning for alpha? If this is alpha, then the x1 component will be u cos alpha. Next two component will be u sine alpha. Okay, so from that you know that this also represents uniform flow, but not in the x-axis, not in the y-axis, but at an angle alpha. So alpha is you now give that meaning to this parameter alpha in the expression that was given to you. So you are given that f is equal to u e to the power minus I alpha z, and asked for what potential flow geometry is that a solution? And the answer is, it is a free stream velocity with a constant velocity u and a constant angle alpha to the x-axis. Okay? Any questions on that? Example 3. Now what we are doing is we are considering a nonlinear function, z to the power n, not z, but z to the power n. N could be greater than or equal to 1. Could also be equal to 1. So when it is equal to 1, you should get the previous result that we get. Now the question is, what is the meaning of u and what is the meaning of n? We don't know to begin with. You need to analyze the problem and then put a geometry around it to see for what geometry, what does the flow field look like. Okay? So here I'm going to do this in cylindrical frame. So I'm going to use that z is equal to r e to the power I theta. Why? Because otherwise I have to do a binomial expansion in x and y or x1 and x2. Okay. Here I can use the De Moivre's theorem to relate e to the power I theta to cos theta plus I sin theta. So it is r to the power n cos n theta plus I sin n theta. And so the real part is u r to the power n cos n theta, and the imaginary part is u r to the power n sin n theta. So once again, very easy to separate the velocity potential and the streamlines, the stream function. They will satisfy the Laplace equations. You can verify that, and they will satisfy the condition of irrotationality and the condition of continuity. Now we have to interpret what does it mean. Okay, so one way of doing that, typical way of doing that, is map out some streamlines to sketch it out. For example, when does the streamline equal to 0? In this expression, when n is equal to 0, sine 0 is 0, right? So that could represent a streamline. Okay, and similarly, whenever n is equal to pi, theta here is equal to pi over n. Okay, this theta is equal to pi over n. The n and n will cancel out. Sine pi is also 0. Okay, so that line will turn out to be a line like this with an angle of pi over n. So you can now give it meaning to the value of n. What is n? N is certain angle sector that is swept by it, where the streamline could again become 0. Okay, so it turns out that this particular function represents flow past wedged sectors. So if you have a plate like this and another plate like that, and you have a flow, the streamlines could be something like this. Okay, and so this angle could be changed. You could have, for example, this angle being 90 degrees. Then you will have streamlines like this. And that will be your stagnation flow, a flow that impinges on a plate and is deflected. Okay, so to get the process for the velocity field, it's basically the same. You have three choices: either use psi in the definition, or use phi in the definition, or take the derivative of f with respect to z, which is nu z to the power n minus 1. And remember, you must extract e to the power minus I theta. And whatever is left, split it into its real and imaginary part. The real part gives you ur, the imaginary part gives you u theta. So here you are putting z to the power n minus 1, which is I to the power I n minus 1 theta, and of course r to the power n minus 1. All we are doing is substituting z equals r e to the power I theta. Okay, and then you have n u r to the power n minus 1. And what you need to observe carefully is this term has e to the power minus I theta. And then what is left with is e to the power n theta. So we're splitting it into two parts. E to the power minus I theta, which comes from this minus I theta. And then e to the power I n theta, which is this part. Okay? R to the power n minus 1 stays as it is. So we have extracted e to the power minus I theta. Whatever is left, you split it into its real and imaginary part. And that will give you Vr and V theta directly. Okay, so we have extracted e to the power minus I theta, and whatever is left, we split it into the real and imaginary part. I think once again I have a typo there. Let's see. This is not a deliberate typo, but who can catch what the error is? There is a typo somewhere there. E to the power I n theta is what? Cos n theta plus I sin n theta. So there must be an I there. Okay. And then the real part is cos n theta. Cos n theta times n u r to the power n minus 1. And the imaginary part is sin n theta. That gives you V theta. Okay, so you get Vr and V theta. Do you get an idea on how to solve potential flow problems now or not? Yeah.
The straight lines like that.
Yeah, I probably jumped a bit ahead and showed you that the streamlines look like this. But the way that you get that is only by plotting the contour. Okay, you have to go to Maple and plot it, or in your mind do this thought process, that is, fix the value for psi here, fix the value for theta, and solve for r, and set a series of points, and then you have to connect them. With a calculator, you have to do that. Or you have to go to Maple and put that one. So you need to actually map out this function to see that it is like this. So all I can show from this expression is at these two values of theta, stream function is 0. So these two are legitimate streamlines. Okay, and the other streamlines are non-zero values of streamlines. But the next part here, we actually show how does the velocity field look like. Why does I put an arrow like this? Is that arrow right? Why does the velocity go into the sector one end and come out of the sector at the other end? You can get all those by looking at this. For example, sine n theta is positive for theta between 0 and pi over n. So v theta is negative. Okay, v theta is negative means you must have a v theta component in this direction because I'm measuring theta in that direction, positive. Okay, and similarly, cos n theta is positive for theta between 0 and pi over 2n. So VR is positive. Okay, and from pi over 2n to pi over n, VR is negative. So VR positive means it's going out. VR negative means it is coming in. Okay, so I'm dividing this into two segments, pi over 2n and pi over 2n to pi over n. Right? And in one segment I'm showing VR is negative, in the other segment I'm showing VR is positive. That tells us that the streamlines must have this kind of a flow behavior, coming in one and going out. And v theta is always negative in that quadrant. If you go to the other quadrant and do the same analysis, you'll get a very similar pattern that is consistent with this. Okay, so that kind of an argument is the one that establishes what the flow directions are. Even if you ask Maple to plot the streamlines, it's just going to give you the set of curves, but you don't know which the direction of the flow. So you need to go through this to figure out what are the directions of the flow. Okay, here how to plot the contours in Cartesian in cylindrical coordinates. So you need to specify coordinate is cylindrical and then give the expression and the range in r and in theta. So this is for selection of a particular value of n, which is the stagnation flow. So in this case, what happens is that it is as if the liquid is impinging and then diverting. Okay, so you could have a plate here. What would be the velocity on this plate? You can calculate that. It won't be 0. Okay, in fact, if you go to the expression for VR and V theta, when R is equal to 0, that is at the center, right? You will find at that particular point, it's a stagnation point. Both velocities will be 0, okay? But at any other value, and in fact, you can do only for this geometry in Cartesian frame also. Any other sector, any other angle, it's best to do it in cylindrical coordinates. For this one, Cartesian and cylindrical will work the same. Okay, and you will find that this velocity is 0. Both velocity components are 0 at that point. So that point is called a stagnation point. And such flows are called stagnation flows. Okay? And of course, the velocity will increase, slip on the plate. If you put a plate, you'll still have a slip velocity right on that in the potential flow. And this, I think, is just the potential function, stream function and potential function. And in the book by Kundu, I think Bernstein and Lightfoot don't spend a lot of time on potential flows. Just a few examples. But in Kundu, they have the sketch for various angles. Alpha equals pi over 3, alpha equals pi over 2, 2 pi over 3, etc. So all these classes of entire class of flows past back sectors, whether it is obtuse or acute, we can calculate the potential flow from that single solution that we have, single function that we have, z to the power n. What is this one? Okay, well, alpha is equal to, alpha is the angle. Okay, this is equal to pi over 3, pi over 2. So this would be 2 pi. Okay, so it is as if you have a plate, and so the fluid is coming from here and going around that plate. So that would be your streamline. Now remember, these are your potential lines. Potential lines and streamlines should always be perpendicular to each other. That's what it's showing here. All the dotted lines are potential lines, all the solid lines are streamlines. Okay, stagnation flow is a special case when n is equal to 2. Okay, and that is the flow where you have an object like this, a geometry like this. So then z is equal to 2. So in this function, f is equal to u z to the power n, we put n equal to 2, so z squared. Okay, and so for that particular case, phi becomes u r square cos 2 theta, which you can also translate into Cartesian frame, which will be x squared minus y squared. Similarly, psi, from the previous expression we have, put n equal to 2, you'll get u r squared sine 2 theta, which you can use trigonometric identity to write it as 2 sine theta cos theta, which you can write as 2u times xy. Okay, and similarly for u1, you can get it in one of three ways. Either you take the psi, put it in its definition, or take phi, put it in its definition, or take the derivative. Okay, when you take the derivative, it is 2uz, because it is a z squared, it becomes 2uz, and z write z as x plus iy, so you get 2ux for u1 minus 2uy for u2. Okay, and at x1 equal to 0, x2 equal to 0, or xy equal to 0, both the velocity components are 0. That's your stagnation point. Once you have obtained these two velocities, v1 and v2, you can get the pressure, as I said, from the Bernoulli equation. So in this particular case, all it is P equals P0 minus 2 rho u square x square plus y square. How did I get that? I simply substituted for v1 and v2. Take the dot product. So it's simply v1 square plus v2 square. That is 2u square x square plus 2u square y square. So I take 2u square constant out, and I get x square plus y square. P0 is some reference pressure, okay, because this must be constant. So I don't know where the constant is. So I evaluate the constant by putting x equal to 0, y equal to 0, call that as P0. So P0 would be this pressure, stagnation pressure. So if I know the stagnation pressure, I can calculate the pressure field at any other point from the Bernoulli equation after I obtained V1 and V2. Here I have a question for you to think about. The statement I make is that the above solution not only satisfies the Euler equation. We know that these velocity fields, the pressure fields, if I take them and put it into the Euler equation, it will satisfy that. Okay. It turns out that they will not only satisfy the Euler equation, but they will satisfy the complete Navier-Stokes equation, including the viscous term. That is, including this term. You can take these velocity fields, plug it in there, and you will find that it is equal to 0. Okay. So the question is, why is Euler solution not a solution to the full Navier-Stokes equation? Do you follow my question? The argument that I'm advancing is any solution to the potential flow problem that I have given so far obviously satisfies the Euler equation, but if you take it and plug it into the Navier-Stokes equation, it will also satisfy the Navier-Stokes equation. So one can argue that all these functions satisfy the Navier-Stokes equation. So then why is it not a solution to the real fluid problem? In fact, I show that if V is given as the gradient of some potential function, I evaluate this term in general for any potential function. Nu times del square V is nu times del square V. V is given as gradient of phi. Okay, so I use the index notation and then I switch the indices out, and then I have d squared phi dxi dxi. But I know that this is automatically 0, right? Every potential function will satisfy the Laplace equation. So this term would identically be equal to 0 for every solution that I have examined so far. That's, I claim so far satisfies Euler equation, but now I'm showing that it also satisfies the full Navier-Stokes equation. And the question that I'm asking you is why? I guess the answer is also there, because it does not satisfy the no slip condition. Every function that we have solved so far for the sectors, for the uniform flow, will also satisfy the full Navier-Stokes equation, even though it was not our intention. Okay? It turns out that because of this definition, it satisfies the Laplace equation. That means the neglected term will automatically be 0. So it will also satisfy the full Navier-Stokes equation, but it will not satisfy the no-slip condition. So these are not full solutions of the real problem. These are still idealized solutions for ideal fluids, fluids that have 0 viscosity. Any questions on that?
They have 0 viscosity.
0 viscosity is what we call an ideal fluid. So there is really no fluid with 0 viscosity, even though people claim that helium, for example, at very, very, very low temperatures, close to absolute 0, behaves in a very strange way as an ideal fluid. It comes closest to the ideal fluid. You can pump it without any friction, that kind of thing. So in that limit, some strange physics happens. Superconductivity occurs in that limit. So in the same way, there are some evidence that they may be acting like an idealized fluid with almost 0 viscosity.
Viscous heating term.
Very slow, viscous?
Viscous heating.
Yeah. Such fluids, if they exist, they don't have any viscous heating because there is no friction, right? But as I said, they don't exist in reality except maybe in that extreme limit. And so this is an idealization. And the key point I want to drive here is that all the potential flow solutions will satisfy the full Navier-Stokes equation, but they don't satisfy the no-slip condition, so they are not real solutions to real fluids. Okay, so that's where the boundary layer theory will come and help us resolve that conflict. Okay, let's do one last example very quickly, and then I have a number of examples that I'm not going to go through in the class, but I put it in the notes and as a reading assignment. So I want you to go through that and understand what each function is. Basically, there is no limit to it. There is a whole book devoted to complex variables that takes different complex variables and analyzes for what geometry it would be a solution. Okay, so here we are taking, now because these equations del square psi and del square phi equal to 0 or linear, what that means is if I have a number of different solutions, I can add them up, I can superpose. And the superposed solution, the added solution, will also satisfy these equations. Linearity allows you to superpose the solutions. So I have analyzed one function already, which is u times z. Now I'm analyzing a different function, a square over z, and I'm adding them up, in fact. So the function I want to analyze is f of z is equal to u times z plus a square over z. For what geometry is that a potential flow solution? That is a question. Okay, and here u is a constant and a is a constant. What is the meaning for a? What is the meaning for u? We need to discover that after the analysis. The procedure is basically the same. Once again, we are going to use cylindrical coordinates. So wherever you have z, you substitute by r e to the power I theta. So here r to the power minus 1, because z appears in the denominator, e to the power minus I theta. Then do the expansion. The expansion is r cos theta plus I sin theta plus a square times r to the power minus 1, which remains the same. But e to the power minus I theta is r cos theta minus r sin theta. Sorry, there is no r there. R is already, that's another error there. It must have been, that shouldn't exist because that's simply e to the power minus I theta, which is cos theta minus I sin theta. The next step is collect the real terms and collect the imaginary terms. Okay, so when you collect the real terms, you get u r cos theta. There is u r cos theta plus from the next term a square over r cos theta. Okay, so that is the real term coming from the first one here and this. Then take the imaginary term I sin theta, and that gives you this u times r minus, here you have the minus sign, and then a square over r sin theta. So the real part gives you phi, and the imaginary part gives you psi. Now you can begin to map. What would the zero streamline look like? when sine 0 is 0, sine 0 is 0. So obviously the line that goes, this is your origin, this could be a streamline, psi equal to 0, right? When, under what other condition psi would be 0? Sine pi, right? So that could be a streamline. So this entire thing could be a streamline. What are the conditions? What about when r is equal to a for all values of theta? It is 0 too, right? So if I take a for all values of theta, means I can draw that, because that is r equal to a for all values of theta. That's how I get a cylinder. So this represents potential flow past a cylinder if you take only the outside. If you take the inside, you have to give it a different interpretation. It's probably like a flow due to a sink or a source, okay? A sink under source, because whatever it produces inside is sucked up inside itself. So remember, along a stream, across a streamline, there is no velocity, there is no cross flow, because by definition, streamline is one that has tangent velocity vector, okay? So the fluid that is inside, if there is any fluid that is caught, it cannot go out. And the fluid that is outside cannot go in. And then you can ask the question, what are the other streamlines that I can plot? That's not going to be so obvious, okay? You need to pick a value of the stream function psi, and pick a value of r and calculate for theta, or pick a value of theta and solve for r and plot those points. And you'll find that the streamlines look like this. These are psi 1, psi 2, etc. So you give this an interpretation that it is the flow, ideal flow, potential flow past a circular cylinder. Now to get the velocity vector, you take the derivative of the stream function, this derivative of the analytic function f, which is, remember, the function is z. So the derivative of this z is simply 1. And the second term is a square over z. Derivative of 1 over z is minus 1 over z squared. Okay, and then you still need to separate, and when you're separating it, you need to make sure that you extract e to the power minus I theta and look at what is left and split that into its real and imaginary part, and that gives you ur and u theta. So ur is this and u theta is this, after you have extracted e to the power I theta out. Whatever is remaining is separated into real and imaginary part. Now you can say, okay, I can put directions, okay, because I can calculate the magnitude of ur, where it is positive and where it is negative, and u theta, where it is positive and where it is negative. Okay. So it says sketch the flow pattern, but I think I guess I left the space for that, but I just given you this flow pattern. That's how it looks like. So it will be like this. Psi equal to 0, this is psi 1, psi 2, etc. Okay. Once we have this velocity field, we have the velocity field, the stream function field, etc. So here are the velocities. So you can take that and put it into Bernoulli equation and get the pressure field. Okay, so this is the Bernoulli equation. So substitute for V dot V, which is going to be V dot V is going to be equal to VR squared plus V theta square. Okay, so we already know VR and V theta. So when you substitute that, you're going to get this humongous expression. Okay, but you need to evaluate this constant. So this P0 is a pressure at some stagnation point. Then you can calculate the pressure at any other point from the system, from this function. And you can integrate that pressure to calculate the net force exerted by such a fluid. An interesting thing is, even though we said that there is no shear force, can there be a net force exerted by such a fluid on a particle? The answer in general is yes, because that will be calculated from this pressure distribution. Okay, in this particular case, the irrotational pressure distribution, when you plot this function, turns out to be like this. That's the irrotational flow. The real fluid, but remember, we started saying, Euler equation is valid for very large Reynolds number when viscosity is very small. Okay, so if you take a real fluid, and this people have measured it, this is how the real velocity, the pressure field looks like. This is for Reynolds number of 10 to the 5. Okay, so there are differences for bluff objects like this that are round. It agrees reasonably well in the front end, but near the separation zone, it differs quite significantly because there is a separation that is occurring in real fluid. In this potential flow, it doesn't occur. And how do I calculate the force? I calculate the force the same way as before. The stress dotted with K in the direction of the velocity field U. Okay, evaluated at R equal to A on the surface of the cylinder. But Tn here, the stress, is nothing but pressure because there is no shear. It's simply minus Np dot K. But I have already found out what P is. Okay, so when I calculate this, plug in that expression and evaluate the integral, I get the integral to be equal to 0. Why is that? This is called the Lambert's paradox. There is no form drag for flow past a potential flow. That's because if you look at the pressure field, you will notice that it is symmetric. Whatever the pressure that is applied in the front is the same as the pressure that is applied from the back of the cylinder. So they basically cancel out. But for any other shape of the object, you will find a net pressure, okay, a net force. And in fact, the place where this is used most often is in aerodynamic objects. If I have a plain wing like that and I integrate this pressure distribution around it, I will get a net pressure that is non-zero, and I can get the direction for the net pressure, okay, and that would be the lift force. If I resolve it in the vertical direction, that will be the lift force, and that prediction is very accurate for these kinds of shapes of objects. But for cylindrical objects like this, as you can see, the error is already large between the actual pressure field and what is calculated from the irrotational flow. Okay, this is the section for self-study. What I have done here is I have given a lot of these complex functions, m over 2 pi log z. Take that, go through the splitting of it into real and imaginary part, Vr and V theta, calculate the pressure, and map out for what geometry it is a solution. So I have about 4 or 5 examples that I want you to study on your own. I'm not going to cover those. And in the next lecture, I will start off with all these you need to study by yourself for the final exam. I'm going to start off with Baudelaire theory on Thursday. Okay? I will stop there.